Welcome to the deep dive. Today, we're cracking open some material that really gets into something essential for modern life, keeping the power grid up and running.
Yeah, making sure the lights stay on.
Exactly. We've got this presentation here, brief overview of power system stability. And what we want to do is, well, walk you through it. We'll go concept by concept, try to unpack what stability really means, why it's so important, and, how engineers actually manage to keep this huge, incredibly complex system balanced.
That's right. And power system stability, you can think of it as the grid's resilience, really. Its ability to handle disturbances, whether they're small bumps or, major jolts,
Right.
and then return to a stable operating state. Keeps everything working correctly. It's fundamental stuff in power systems.
Yeah, it sounds like it.
And this presentation, it does a pretty good job laying out the main ideas, the different sides to the challenge. So yeah, we'll guide you through, point out the key things.
Absolutely. So settle in, because we're about to get into the physics, the engineering.
Right.
Basically what stops blackouts and keeps everything powered up. Let's jump into the material. Okay, starting with these initial slides, the presentation dives right in. It says stability, at its core, is about maintaining equilibrium between opposing forces. So in a power system context, what are these opposing forces the material's talking about?
Okay, so the fundamental balance here is between the total power being generated
Right.
and the total power being consumed. So all the loads plus, and this is important, plus any energy that's lost just moving the power around.
The losses in the lines and
Yeah,
stuff.
exactly. The transmission, the distribution network. Think of it like a massive, constantly shifting scale. Generation on one side, pushing power in,
Yeah.
and everything using power on the other. Lights,
Yeah.
factories, your phone charger pulling power out, plus those line losses taking a cut.
So stability, then, as it's defined here, is about hitting that balance point and, crucially, staying there or getting back there quickly, whether things are running normally or after something, kicks the system.
Precisely. And it's not just about the total megawatts matching up. The material, it digs a bit deeper into what makes a power system stable. It lays out three key conditions.
Yeah.
First, generation has to continuously equal load plus losses. That's the energy balance. Second, all the key operating parameters, things like voltage levels everywhere and the system frequency, 50 or 60 hertz.
Right, the standard frequency.
They all have to stay within pretty strict acceptable limits. Those limits protect the equipment, make sure things work right. And third, maybe the most critical point, all the major components, especially those big rotating generators, they have to stay in synchronism.
Synchronism. Okay, that sounds
One
important.
of absolutely vital.
And the material points out, this isn't a small system we're talking about. Thousands of generators, thousands of kilometers of lines, millions of loads.
Massive.
Keeping all of that in sync within those tight voltage and frequency bands, that sounds like an incredible challenge.
It is. It's a monumental engineering feat, really. Maintaining that coordination, that balance in real time across something so spread out and dynamic.
Wow.
And to understand how power actually moves around this network and how that connects to synchronism, the presentation introduces a really fundamental tool, the power transfer equation.
Ah, yes, the equation. P equals V's times VR over X times sin delta. Let's break that down. P is the active power moving between 2 points.
Yep.
V's and VR are the voltages at the sending and receiving ends. X is the impedance of the path, like the resistance to flow.
Sort of, yeah. Impedance is the total opposition in AC, combining resistance and reactance. It's what limits the flow.
Got it. And then delta, the voltage angle difference, also called torque angle or power angle. And the material really stresses this angle controls the power flow.
That angle, delta, it's absolutely key in AC power systems, especially for those big synchronous machines. It's the phase difference between the voltage waves at the 2 points you're looking at.
Okay.
And it's not just theoretical. In a generator, it relates directly to the physical angle between the rotor's magnetic field and the stator's field, which is tied to the grid. This angle determines the electrical torque and therefore how much active power flows out.
So it's physically meaningful.
Very much so.
Huh.
And the presentation rightly points out system operators, the control systems, they need to influence or manage this angle to control power flow and keep things stable.
And the material shows that classic power angle curve. It's sine wave, right? Shows power transfer increasing with the angle up to a maximum P max when delta hits 90 degrees. What's that curve telling us visually?
That's a great visual. It shows exactly that relationship. As delta increases from zero, the power you can push increases following that sine curve. It hits the theoretical peak, Pmax, at 90 degrees.
And Pmax depends on the voltages and the line impedance.
Correct. V's, VR, and X set that maximum ceiling. But the critical part for stability is what happens after 90 degrees.
Right, the curve drops off.
It does. If the angle goes past 90 degrees, the power transfer capability actually decreases. And that's fundamentally unstable territory for traditional generators.
Why unstable?
Because if a disturbance pushes the angle past 90, the electrical torque that's supposed to pull it back actually gets weaker, not stronger. So the angle just keeps increasing faster and faster. You lose synchronism.
Ah, okay.
So operating well below 90 degrees, that gives you your stability margin. The bigger the gap between your operating angle and 90, the more disturbance you can ride through.
Got it. The presentation then moves into major concepts driving power system stability. First one mentioned is operating and non-operating areas. What's that about?
Yeah, this is about how we often view the grid. It's usually divided into different control areas or operating regions. Think of like different utility territories tied together.
Okay.
Stability often involves making sure these different areas stay synchronized with each other and that power can flow reliably between them. Each area might have its own mix of generation and load, its own controls, but they're all connected. So you need to ensure a problem in one area doesn't destabilize its neighbors or cause the connections to break. Non-operating areas would just be parts temporarily disconnected, maybe for maintenance.
Makes sense. Next concept. Rotating mass equilibrium. Balancing mechanical and electrical torque. This seems to get to the heart of traditional generators.
It really does. Think about a big generator steam, hydro, gas turbine driven. The turbine provides mechanical power, creating a torque that spins the generator's rotor.
Right, the input power.
Exactly. And the generator stator, connected to the grid, produces electrical power output. This output creates an opposing electrical torque on the rotor. These two torques, mechanical input and electrical output, are constantly playing tug of war.
And ideally, they're perfectly balanced.
In steady operation, yes, mechanical torque in equals electrical torque out. But as the material points out, if something changes suddenly...
Like a fault, or load suddenly jumping.
Exactly. Or maybe the turbine input changes. If that balance gets disrupted, say electrical torque drops, but mechanical stays the same, you get an imbalance, a net torque. And that net torque is called the acceleration torque.
Okay, acceleration torque.
And what does it accelerate? The huge rotating mass of the generator rotor. It either speeds up or slows down relative to the grid's synchronous speed.
And that's what changes the power angle delta over time.
That's the direct link. The change in angle is the system's dynamic response to that torque imbalance. How the system handles these imbalances, whether it can damp down those accelerations before the angle gets too big. That's crucial for stability, especially rotor angle stability.
Okay, another major concept, load generation balance. And the presentation links this directly to frequency.
Yes, this is probably the most intuitive one. In an AC grid, the total active power being generated must, at every single instant, match the total active power being consumed by loads, plus those system losses we mentioned.
Instantaneously.
Wow. Instantaneously. And the system-wide indicator of this balance is the frequency. If generation exactly equals load plus losses, frequency holds steady at its target 50 hertz, 60 hertz, whatever the system standard is.
So if generation suddenly pulls ahead of load, frequency goes up.
Frequency rises. Too much power being pushed in, the whole system speeds up slightly.
And if load overtakes generation?
Frequency drops. Not enough power, the system slows down as loads pull energy out of the rotating inertia.
Okay. The presentation lists the players here. Mechanical power, inverter-based power, like solar, wind, electrical power, two loads, and losses. Keeping frequency steady means keeping that equation balanced.
Precisely. And the material also mentions storage batteries, pumped hydro playing a bigger role now because they can react very quickly to inject or absorb power to help smooth out those imbalances and stabilize frequency.
Right. The final concept here is synchronizing and damping torque. Electrical torque has these two components. Tell us about those.
Yeah, these are super important for how the system reacts dynamically. Synchronizing torque, first off, that's the component of electrical torque that acts like a restoring force.
Like a spring.
Exactly like a spring. When a generator's rotor angle starts to drift away from its stable position relative to the grid, synchronizing torque tries to pull it back. It's what fundamentally keeps the machines locked in sync.
Okay, keeps them together. What about damping torque?
Damping torque is different. It acts like a shock absorber. It's the component of torque that opposes the motion or the speed of the oscillations.
Ah, so it fights the swinging.
Precisely. It dissipates the energy of those swings, making the oscillations die out quickly. Without enough damping torque, even a small disturbance could set off rotor angle swings that just keep going, or worse, grow bigger and bigger until things fall apart.
Okay, I see.
So the presentation emphasizes you need both: synchronizing torque to provide the spring that holds things together, and damping torque to provide the shock absorption that settles things down quickly after a bump.
That makes sense. Now, the presentation shows two ways to classify stability: an old classification and a new classification. Let's look at the old way first.
Okay, so the old classification, as presented here, mainly categorized stability based on the grid we had for, well, most of the last century, dominated by big synchronous generators.
Right.
The main branches were rotor angle stability, frequency stability, and voltage stability. Pretty clear categories.
And rotor angle stability is about keeping those rotating machines synchronized. It's broken down into steady state, transient, and dynamic stability.
Correct. Steady state deals with stability under small, slow changes. Think gradual load increases. Transient deals with stability after large, sudden events like faults, big disturbances. And dynamic stability, also called oscillatory stability, is about damping out those low-frequency swings that can happen after small disturbances. It's about having enough damping torque.
So steady state and transient are more about having enough synchronizing torque to stay locked in or pull back,
Generally, yes. Lack of synchronizing torque is the main issue there.
while dynamic is about lack of damping torque, letting oscillations run wild.
That's a good way to put it for the old classification.
Yeah.
Then you had frequency stability, keeping the overall generation and load-balanced active power balance, and voltage stability, maintaining voltage levels, which is tied to reactive power balance.
And the presentation notes, large disturbances are things like faults, switching. Small disturbances are more like load fluctuations, reactive power variations. Seems quite thorough for the traditional grid.
It was. It served well for decades. But the grid isn't just traditional anymore, right? We have all this new tech coming online.
Renewables, batteries.
Exactly. Which leads us to the new classification shown on the next slide.
Right. And this one, it keeps rotor angle, frequency, and voltage stability, but adds two new categories: converter-driven stability and resonance stability. And it specifically mentions the system now includes synchronous generators plus dynamic loads and converter interface generation technologies, CIGs, loads, and transmission devices. This sounds like it's explicitly bringing in the power electronics.
That's precisely the point. The new classification acknowledges that a huge chunk of new generation, storage, and even some loads and transmission devices connect to the grid through power electronic converters, not directly rotating machines.
So things like solar panels, wind turbines, batteries, HVDC.
All of those.
Yeah.
And these converter interface resources, or CIGs, or sometimes called IBRs, inverter-based resources, they behave very differently dynamically than traditional generators. Their response is dictated by control software, not inherent physics like inertia.
Okay, so converter-driven stability must be about issues arising from these new devices.
Yeah. Exactly. The presentation mentions fast interaction and slow interaction. Fast interactions might involve, say, rapid oscillations caused by the interaction between a powerful FAT-gas device like a STATCOM and a weak part of the grid. Very quick phenomena. Slow interactions could involve the control loops within the converters themselves, the phase-locked loops that sync them to the grid, or their voltage and power controllers. If these aren't tuned right, they can interact badly with each other, or the grid, potentially causing instability over seconds or minutes.
And resonance stability. It lists electrical resonance, mentioning deified wind turbines, and torsional resonance with HVDC and FACS.
Right. Resonance is about oscillations getting amplified at specific frequencies. Electrical resonance can happen if the electrical characteristics of the converters interact with the grid impedance in just the wrong way.
Okay.
Torsional resonance is about mechanical vibrations in the shafts of rotating machines. Certain power electronic devices, like HVDC converters, can sometimes excite these mechanical vibrations if not carefully designed and controlled.
So the new classification basically says stability is now about both the old electromechanical stuff and these new, faster, control-driven dynamics from IBRs. The system dynamics are electromechanical plus IBR dynamic.
That's the takeaway. We need this broader view to understand and manage stability in the modern grid. It's more complex now.
Definitely sounds like it. Okay.
In next in series, we will discuss on angular stability, which includes steady state, transient and oscillatory stability issues in power system.